Good morning, good afternoon, good evening, everyone. I think we can begin now. I see quite a few of you already here. I have the pleasure to welcome you to today's webinar focusing on exploring ammonia as a shipping fuel and its potential impact on the nitrogen cycle. This webinar has been organized by the Global Partnership on Nutrient Management as part of a series of information sharing technical webinars. The webinar today aims to showcase the efforts to balance the environmental benefits of using ammonia as a shipping fuel and its potential impacts on the global nitrogen cycle. My name is Stephanie van der Poel, and I will be your moderator for today. I work in the Source to Sea Pollution Unit at UNEP in Nairobi. Without further ado, it is my great pleasure that I introduce to you Professor Mark Sutton, environmental physicist at the UK Centre for Ecology and Hydrology and the Vice Chair of the Global Partnership on Nutrient Management. Please go ahead, Mark.
Yeah, thanks very much, Steph, and a pleasure to have you all on the call today. Some of you I can see, those who are panelists. There's around 80 of you that I cannot see, but welcome all 80 of you, and I can see that that number's still going up, indicating a great interest in this topic. So I'm going to tell you first a little bit about the Global Partnership on Nutrient Management and then about our call today. So the GPNM, as we call it, is a multi-actor partnership from academia, business, civil society, governments looking together at the global nutrient challenge. In terms of the nutrients, we spend a lot of time talking about nitrogen, but there's also phosphorus, potassium, all the micronutrients running in those biogeochemical systems around the world, multiply under threat. Our first challenge is often a conversation about agriculture, but of course nutrients are not only a conversation about agriculture, there are also issues in water pollution, water sources as well, although UNEP also has a global wastewater initiative. So in GPNM, the point is to work together and learn together to provide a space where there can be more conversation than there typically is in a normal UN system. We're complemented by the Nitrogen Working Group of the United Nations Environment Programme, which was established following the first resolution on sustainable nitrogen management in 2019, Resolution 414, and followed up by Resolution 52. Those only cover nitrogen, but that is an emerging intergovernmental process talking about nutrients. We don't have a global intergovernmental process about other nutrients, but GPNM is there, ready to stimulate that conversation and support the member states in that. And of course, it's not just about member states, it's about practice change, and that's why all of you on the call and all the practitioners speaking to us today are important. So I want to just mention that the Global Partnership on Nutrient Management is looking towards gaining new members. And if you have a look in the chat in a minute, our colleague Vanjiru will put in the link whereby you can sign up and find out more about the Global Partnership on Nutrient Management and how to join it. So the topic for today, the charting the course on the ammonia from a shipping fuel. Of course, this is part of the transition about going away from fossil fuels towards alternative energy sources. That might mean using ammonia in many ways, not just shipping. So we've taken ammonia in shipping as our focus. We might hear a bit as we go along, a bit more about that wider context of ammonia also as a fuel more widely. Of course, it's only going to be possible once we can use so-called green ammonia, by which we mean ammonia from renewable energy sources, as compared with typical brown ammonia from fossil fuel. There's no point to attempt to avoid fossil fuels by making a fuel in the first place from the fossil fuel. So clearly that transition is towards renewable energy. But of course, that's a great opportunity, but also risks. And we're going to hear today more about the environmental risks. And that's obviously particularly relevant for the United Nations Environment Programme. And among those risks, of course, are risks at sea, and very happy that we also have with us the International Maritime Organization, a sister organization to the United Nations Environment Programme, who will give us their take on the challenge. Finally, one more issue, and I'm not sure we're going to hear about it today, but we have heard a little bit in conversations about how this might completely transform the world system for ammonia. So whereas the major use of ammonia has been for fertilizers in the past, could this big demand for using ammonia as a fuel actually change the whole price system? Could it mean that nitrogen prices end up going up, making it on the one hand harder for farmers to avoid fertilizers, and on the other hand, make governments more strongly motivated to take action? Well, I'm not sure we're going to cover that, but let's see if anybody has anything to say. And with that, we look forward to hearing all of you panelists what you have to say. Thanks very much for joining us, and I'm going to hand back over to Steph.
Thank you so much, Mark, for setting the scene. We will now move on to the presentations, but followed by a question and answer session. Each panelist will make a presentation of 15 minutes, which will then leave us with 15 minutes to dive into the question and answers. We would like for this webinar to be as interactive as possible, so we invite you to put your questions in the chat box, which will later be raised during the Q&A session. So we're going to start with the first presentation. We'll begin the panel discussion with a presentation from the Ammonia Energy Association. Vibeke Rasmussen, she has over 25 years of industrial experience in the water and fertilizer industry. She joined Yara in 2014, where she has been responsible for research and environmental impact, circular economy, and fertilizer product quality prior to her current role as EVP President-elect of the Ammonia Energy Association. Vibeke, please go ahead.
Thank you very much for that. And it's a pleasure to be here today to represent the Ammonia Energy Association and to talk a bit about ammonia's role in the energy transition as we see it. I think just to say also that the Ammonia Energy Association has grown tremendously over the last years, which is also showing that there are a lot of attention, of course, that ammonia is getting in this transition. I think we will start with really saying that even though now we're talking about the energy transition and hydrogen derivatives, which ammonia is one of, seems to be something that a lot of people think is something new. We would just say that ammonia is really everywhere and in use in large quantities already today. It exists sort of naturally in biological systems, microbes in the world today already, and it's present everywhere. As you know, it's a key nutrient, and it's also the second, I think it's still the second largest man-made chemical annually, globally, which of the largest part of that goes into fertilizer production. So it's an essential nutrient, of course, also for our food and the world food production. And now it's almost coming up also as very important as part of the energy transition, and mainly because, of course, ammonia can be combusted without any CO2 emission. And that's why also it's promising as a fuel for the future and for the maritime and for other sectors that are decarbonizing. I would say today the global production of ammonia is about 185 million tons, where 80 to 85% of that is actually fertilizers. The rest is for other chemical uses as a refrigerant and other uses of ammonia today. And it actually does contribute with about 1% of the global greenhouse gas emissions. And that is, as was said also at the beginning, is because today ammonia across the world is predominantly produced from either coal or from natural gas in steam methane reforming. So the production of ammonia is emitting, of course, CO2, and it's the transition of ammonia into the future where you would either have pathways which would capture the CO2 and permanently store it to reduce the CO2 emission of ammonia production, or you would go to getting the hydrogen from electrolysis and produce it with renewable energy, where you then cut the emissions in the production pathways and therefore also have a fuel or energy carrier for the future. Is this really growth that is looking to happen into new sectors, which is then shipping industry as a fuel? It's for power generation, where you're looking in parts of the world, you can co-fire ammonia with coal, and then also as a hydrogen carrier. Because transporting hydrogen is much more cumbersome than transporting ammonia. Due to the cryogenic, you have to really lower the temperature of hydrogen down to -250, while as ammonia is liquid at -30. So it's easier to transport hydrogen in the form of ammonia. So these are the three main growth areas, which also means that the prediction in the market research is everything from 3 times to sort of 6, 7, 8 times the growth of today's market. So some of the challenges, of course, in this growth is that ammonia in use and the anthropogenic way of using ammonia is also then having, if you don't combust ammonia to complete an N2, you will form NOx, N2O emissions, and also slips of ammonia. And these are really what we need to contain. And I think that the existing industry and the fertilizer industry is having a high focus of this already today, where there are catalysts to capture NOx, N2O, and we have high focus on ammonia slips. The leakage of ammonia and I would say some of the benefits in some case is also the safety issue and the hazardous content of ammonia, which gives you a high focus on leaks of ammonia and to contain them. And this is sort of a benefit that we can learn from the existing industry that have produced, transported and used ammonia for over 100 years. So it's really to contain these levels and to use the good results that we have from the existing industry when we transform this into new uses of ammonia for the future. And I think a lot of this is already being done. There are a lot of reports. We know there are research going on. What is the emission to air and to sea of ammonia? How can we actually do combustion engines? How do we control the NOx, the N2O emissions? How do we actually control if we have any spills or leakages? And there is a lot of history also in how this has been done and how it can be handled. So this is what we really need to take forward when moving from today's fertilizer industry and into new uses of ammonia. As they say, the safety is essential. It's something that's coming up also when you're going to use ammonia as a fuel. And that is also giving us a good way of controlling the emissions. I think one project that is also coming up is the joint industry project of ARISE, which is looking into the data we have on releases today and to control this. So they want to do a large scale or controlled release into the sea and develop new methods for measurement, control, to have data, to really be doing a modeling tools and everything of what will happen and how can we contain and control potential leakages of ammonia. So I think from the Ammonia Energy Association, our main, I would say, takeaway for this is that we believe that the existing controls that the ammonia industry already have today really need to be transferred into new uses of ammonia. We need to have the good controls, the good regulations, the good safety methodologies that are already in place. Also, when we move into new uses of ammonia. And we need to do more testing and more proof points, and we need better methodologies for also checking and testing of the leakages that might happen. So I think really transfer of knowledge is our key point, and the fact that we really believe that ammonia can have a big role to play in the future energy system as a fuel and as for power production, and not the least as the hydrogen carrier. And we need to ensure that getting, I would say, transferring from one issue of CO2 emission is not creating a new one. So we take really seriously that we need to have controls of all the emissions which can derive from use of ammonia. Thank you.
Thank you very much, Vibeke, for your presentation. Very interesting to hear as well about the predictions. I will now introduce our next speakers from Chalmers University of Technology. We have Fayez Malik. Fayez is pursuing a doctoral degree at Chalmers University of Technology in Sweden, where he is assigned to the research group Maritime Environmental Science. The system-level evaluation of fossil-free fuels for shipping is the primary focus of his research investigation. For the past few years, he has been seeking to understand the environmental and economic performance of various climate impact strategies for shipping from a life cycle perspective, including the utilization of ammonia and other fuels. Fayez, please go ahead.
Thank you, Stephanie. I hope you can hear me. Yeah, starting with the introduction, ammonia in shipping sector is very important for decarbonization, and shipping sector, is a backbone for international trade. And shipping at the same time is responsible for 3% of global carbon dioxide emissions, anthropogenic carbon dioxide emissions. And IMO have devised reduction strategies to reduce greenhouse gas emissions from shipping by 100% by end of 2050. And we have several climate neutral choices, including ammonia, but all ships are different. And most of these technologies, decarbonization technologies, are still under development for the shipping sector. And you should not forget that it's not just climate impact from the shipping. There are a lot of other impacts associated with emissions of NOx, SOx, other particulate matters, and carbon-related molecules, which impacts human health and natural environment. And it's very significant from shipping sector. So coming to several climate choices, we have ammonia, most prominent discussions around ammonia now. Then there are liquid hydrogen, methane, methanol, and several others. But these four are majorly discussed among different climate neutral choices. But to be climate neutral, it should be produced from a climate neutral production pathway also. So there are a lot of discussions like producing green ammonia, for example. It's called ultra-fuels, produced from renewable electricity, or from biomass, if bioammonia, and if it's from blue fuels like natural gas with carbon capture, it's blue ammonia. And similarly, other fuels also can be produced from these pathways. And it's very important that these fuels, to be climate neutral, it should be produced from climate neutral pathways. So coming to our core of the discussion, what's ammonia in shipping looks like. So ammonia, either you can burn directly in an engine and use to propel the ship, or you can use it in fuel cells and then use it to propel the ship using a motor, electric motor. Or you can crack the ammonia, produce hydrogen, and use hydrogen to run the ship using engine or fuel cells. However, it does not stop with that. While using the shipping, volume and weight is a big constraint, because ammonia have lower energy density than the currently used fossil fuels. In our assessment, we found that like for bulk carriers and tankers, it may not affect the cargo space because it can be boarded in the deck. Yeah, but the main concern would be the safety, where ammonia is very toxic and corrosive. So we should ensure that ammonia gas is not released. It may be through scrubbing of vent gas or similar methods. And in case of leakage, there should be a personal protective equipment for the crews and additional safety measures like detection, double-walled pipe, and suppressors. And for passenger, it may be less feasible because the risk of exposure for passengers would be more sensitive. So when you look into a ship now, like the fossil-based ship, you have a lot of emissions, like carbon-based emissions, a lot of greenhouse gases, then also NOx, nitrous oxide, volatile organic compounds, SOx, particulate matters. In addition, there are onshore emissions, which is linked with the production of these fossil fuels associated with the refinery and the extraction. So when you move to ammonia, you eliminate a lot of emissions, mainly the carbon-based emission, because there's no carbon in ammonia. But you may increase the nitrogen-based emissions like ammonia, NOx, and nitrous oxide. And in addition, there will be some other onshore emissions while producing ammonia. So while looking to these emissions, while using the ammonia in shipping and looking to this emission, we should look from a life cycle perspective. That is looking into both when ammonia is used in the ships and also when ammonia is produced onshore. So life cycle perspective is used to assess these things. And from if you look at the system boundary, like well to tank, that's for while producing the ammonia, and tank to wake when it is used in ships. And also you need special equipments in powertrain, like specialized ammonia engines and probably fuel cells. And so you have to replace these components because it's very corrosive. And of course, ship also needs a lot of material and energy. So we looked into this from cost perspective as well as from life cycle perspective. And from the cost perspective, you can see that ammonia have lower cost options compared to other options. And if you see, the cost is a major part of all these fuels. And ammonia can be produced much cheaper than most of the green fuels. And if you look at also the carbon abatement potential, that is the amount of the amount required for reducing 1 ton of carbon dioxide, ammonia still have low carbon abatement cost. This means that ammonia, as such, from economic perspective, is a very prospective fuel in shipping. But still, it's very high because you see 270 euros per ton of carbon dioxide is required for abatement. So when you look into the environmental impact here from the results of the environmental impact, we can see because of the emission of nitrous oxide, the green ammonia have a higher climate impact than most of other green fuels, green hydrogen and green methanol, except for green methane, which have a highest impact due to methane slip. That's from global warming potential perspective. But when you look for the other environmental waste and to the total normalized environmental impact, ammonia have much higher impact than most of other green fuels. And why this is mainly because of the emission of nitrogen-based compounds. So if you look into details, the acidification, due to the acidification is mainly the emission of NOx, which creates acidic compounds in the atmosphere. And also the eutrophication, which when leached into water, it creates eutrophication potential. And for all the fuels, relatively, large resources is required for producing green fuels. And it's not just for ammonia, it's for all the green fuels. Yeah, this is results from the life cycle assessment. So what I will just conclude the main results, like from the cost perspective, ammonia have a lower cost potential among all other green fuels, electro fuels. But however, the safety is a big concern for ammonia, and especially for the safety of the crew and the passenger if ammonia is used as a fuel, as ammonia is toxic. The climate impact of ammonia hugely depends on the emission of nitrous oxide, which is a strong greenhouse gas. So compared to green hydrogen and methanol, ammonia have a higher climate impact. And when you look into other environmental impacts, eutrophication and acidification is a big concern for ammonia. And also higher mineral resource is a concern for these fuels. So these are results from our life cycle studies. And when we compare ammonia with different fuels, and these are the risks associated with ammonia. So thank you so much.
Thank you, Fayaz. That was a very, very interesting presentation. I will now introduce you to our next two speakers. This is Dr. Lucy Gillam from Seas at Risk. She is an environmental scientist. She is an environmental scientist and policy specialist with over 20 years of experience developing science-based policy and campaigns focused on international transport, ocean governance, and ecosystem-based management. Lucy is responsible for Seas at Risk work on shipping and system change. And we will also hear from Tanner Tuttle from Erasmus University. He is an environmental psychologist utilizing system thinking coupled with systemic change interventions to encourage societies to shift to a metabolism that functions within the 9 planetary boundaries with societal safety, social justice, and regeneration of our biosphere. Both are working under Delta Initiative on new fuels for clean shipping, investigating ammonia as a shipping fuel in collaboration with Delft University of Technology and Erasmus University through the lens of planetary boundaries, social justice, and societal safety. Please go ahead.
Wow, that was a mouthful, but you did a great job. Thank you for that. Yeah, so we are performing transdisciplinary research on ammonia as a maritime shipping fuel, and we'll release a white paper later this summer. So for now, we're going to share with you ammonia as a fuel why ammonia as a fuel needs to be urgently looked at and addressed in terms of some foundational issues. And that said, Lucy will take it away and jump into some of the technical details.
Brilliant. Thank you very much. The use of ammonia as a shipping fuel has the potential to reduce emissions if green ammonia is used, and we've heard a lot of detail about that just now. However, there are a number of stumbling blocks and dots that need joining. So one is the safety risks of ammonia because it's caustic, toxic, and dangerous to handle. And I'm not covering that today, but we heard a little bit about that in the first presentation. And secondly, the risk that the fuel switch, which while saving CO2 emissions may result in more potent greenhouse gas emissions from nitrous oxide due to further disruption of the nitrogen cycle, as well as eutrophication, acidification, and air pollution. Ammonia can be an indirect greenhouse gas when it's emitted to the environment as well. So to date, the majority of studies evaluating ammonia as a shipping fuel haven't accounted for the issue of nitrogen cycle disruption and indirect nitrous oxide emissions from ammonia emissions, nor the challenge of dealing with nitrogen permits for infrastructure. Therefore, we welcome this initiative from UNEP and the IMO to explore this problem. Due to fixation of nitrogen for agricultural and industrial uses, the nitrogen cycle is already severely disrupted. The planetary boundary for nitrogen is calculated to be exceeded 3 times over. UNEP recognises this problem and has the Global Nitrogen Partnership and the goal of halving nitrogen inputs to the environment by half by 2030. Losses and efficiencies across the value chain could result in reactive nitrogen emissions, ammonia, NOx, and nitrous oxide, negatively impacting air quality, the environment, human health, and climate. Ammonia releases in the environment can lead to deposition of nitrogen compounds in ecosystems, causing nutrient imbalances and disrupting natural habitats. This can harm plant and animal species and disrupt the ecological balance. And we've heard a bit about eutrophication and acidification described in the paper by Fayaz that we've just heard. And in the EU, this is really important to consider because many countries are already exceeding EU rules for nitrogen emissions and therefore cannot afford to have in increase in nitrogen deposition. But the biggest stumbling block in the efficacy of the ammonia as a climate change mitigation solution is the potential of nitrous oxide that could wipe out any benefits of a fuel switch. Nitrous oxide is a potent and long-lived greenhouse gas with a global warming potential of 265 times more than CO2. So even small fluxes or emissions can have a large consequence on the greenhouse gas budgets and the life cycle analysis. Nitrous oxide also contributes to stratospheric ozone depletion, which is another of our planetary boundaries that we need to be aware of. The primary sources of nitrous oxide from the use of ammonia as a shipping fuel will likely come from combustion-related emissions. So when ammonia is burned in an engine, there will be emissions of unburned ammonia or NOx emissions, as well as potentially some nitrous oxide. Now, these can be controlled by various engine management strategies or by post-combustion selective catalytic reactor technology. However, there is a trade-off between tackling these different nitrogen-containing substances. So measures to reduce one could lead to an increase in another. This means we need to have reliable, transparent data to optimize, which will need to be optimized in real world conditions. And put on a slide here a call from the NGOs asking for transparency on emission data, and also a recent story this week about engine emission data fraud, which has been going on for the last decades. So the secondary indirect sources of nitrous oxide emissions would come from the oxidation of ammonia leakages into the atmosphere, and the biological conversion of nitrogen in the environment following reactive nitrogen deposition. So global climate models estimate about 1% of nitrogen in ammonia gets already converted to nitrous oxide following ammonia reaction in the atmosphere. And the IPCC uses this same emission factor of 1% to estimate the fraction of nitrogen converted to nitrous oxide for greenhouse gas inventories, although research estimates in the literature are highly variable, depending on environmental conditions. So anything from 0.1% to 20% of reactive nitrogen can be converted to nitrous oxide. From atmospheric emission studies, researchers estimate a global emission factor of more than double the current IPCC level of 2.3 of combined direct and indirect emissions. So this larger number suggests that the nitrous oxide emissions may have a non-linear response at a global and regional scales with high levels of nitrogen input. So one of the things that we think is necessary is for an IPCC for nitrogen to track the science and optimize the models. On this topic of indirect emissions of nitrous oxide, the Wolfram et al. 2022 paper calculates that if we had 0.4% of the nitrogen in ammonia used as fuel released as nitrous oxide, then that would wipe out the climate benefits of the switch. Again, this is because of the potency of nitrous oxide, which, remember, is 265 times more heating than CO2. It's also not known the rate of ammonia losses through the industrial supply chains. But if we were to look at the leak rate of methane from LNG supply chains, that's around 2.3%. So if ammonia leaked hypothetically at a similar rate, then you could have indirect nitrous oxide emissions up to 0.46%. So add to this direct emissions from poor combustion strategies, and it could very well be a showstopper. There are also risks of nitrous oxide conversion in marine and aquatic systems. Emissions and deposition of reactive nitrogen, ammonia, NOx, etc., to aquatic and marine systems can lead to nitrous oxide, and emissions of nitrous oxide from aquatic systems are on the rise due to the dramatic increase in nitrogen inputs from human activities. And of course, the majority of those activities are agriculture, but the industrial sources are around 15%, so not insignificant. And we are talking about a massive scaling of industrial sources. The global biogeochemical cycles of nitrogen in marginal oceans are being strongly interfered with. And these are major shipping and transport channels between terrestrial and ocean ecosystems. And this ocean cycling of nitrogen and production of nitrous oxide is rather poorly understood. However, I share a paper here by Babin et al., which shows that oceans are a significant and rising source of nitrous oxide. Given that shipping operates at sea, use of ammonia as a shipping fuel could lead to an increase in reactive nitrogen to ocean and coastal systems, further accelerating these potent nitrous oxide emissions from oceans. So what are our kind of demands? Demand to industry. Well, the negative environmental impacts must be controlled by optimizing engineering and safety and monitoring and transparency on all emissions through the supply chain. We need robust regulation and management strategies. Additionally, careful site selection and consideration of ammonia use in regions with specific environmental sensitivities could reduce ecosystem impacts. In the current ammonia supply chain, there are leaks, spills, and venting from infrastructure, and there is evidence in literature and from our expert interviews that industrial inventories are systematically underreported for ammonia and nitrous oxide emissions. So this gets us on to what are our demands for policymakers? What can the IMO do? Well, we think it's important that IMO regulates for a zero emission system and includes all GHGs, including indirect emissions from ammonia conversion to nitrous oxide in the environment, and fills the gaps in emission life cycle assessment gaps across the entire supply chain, and also to map the regulatory processes that need to be adjusted across the organisation in order to safely do this transition. Also, for the organisation to develop a nitrogen action plan for the shipping industry and feed this into the Global Maritime Nitrogen Partnership work at UNEP. This could also be an opportunity to improve the NOx rules and tackle other sources of nitrogen pollution from the shipping industry, not just from the use of ammonia. We need to have transparency on emissions from shipping engines, and every link in the supply chain need to be aware that we've had this engine scandal, and also that NOx real-world data differs from lab data. So it's important to use externally validated data from real-world conditions, and to play a role in creating awareness amongst policymakers, seafarers, workers, port infrastructures of the risks of nitrogen cycle disruption from this potential fuel option. Finally, to explore liability systems for new fuels. Now, there is an ongoing research with the Committee Maritime International Lawyers to establish alternative fuel liability regimes to include this sort of nitrogen pollution. What can UNEP and UNECE do? Establish an IPCC for nitrogen and better understand nitrous oxide pathways, a UNEA Assembly resolution on nitrogen from combustion sources to include shipping, update the Convention on Long-Range Transboundary Air Pollution and the Gothenburg Protocol to include shipping, combustion sources, and improve monitoring of ammonia and nitrous oxide, perhaps by having improved resolution of these compounds from global satellite monitoring. In summary, ammonia has the potential to be a valuable energy carrier in the transition to low carbon energy systems, but it's essential to consider and manage all environmental and safety risks associated with production, transportation, and its use in a holistic way. We must tighten the screws on the supply chain and also make sure any new entrants understand the need for having high standards. It would be a great shame to expose seafarers and society to the safety risks of ammonia if in the end we had no gain in solving the climate crisis. We hope our transdisciplinary research into ammonia energy systems will play a role in informed decision-making in pursuit of sustainable and clean energy systems. Thank you very much.
Great, thank you for your presentation. I liked how forward-looking your work is on the solutions as well. Thank you very much. So our next presentation is from Princeton University, Rui Wong. She's currently a postdoc at Princeton University. She has been working on utilizing multiple ammonia datasets, including satellite, ground monitoring network, and field campaign data to better understand ammonia emissions from agricultural activities and wildfires at high resolution, as well as ammonia's impact on nitrogen deposition and air quality. Rui, please go ahead.
Thanks for the introduction, and So I'm Roy Wang, and I'm going to talk about environmental impacts of the hydrogen economy, and mostly from the perspective of how can we use ammonia measurements, especially satellite ammonia observations, to better understand the possible ammonia emissions if we are going to switch into a hydrogen economy. And I want to say thank you to all of my co-authors listed here. So nitrogen could be converted into reactive nitrogen through nitrogen fixation, and in natural environment, it's done by lightning and plants and oceans. And for anthropogenic parts, it's mostly from agriculture, fertilizer production, and combustions. So the figure here is from our recently published paper, shows that the estimated reactive nitrogen emissions from the ammonia economy. So we assume that ammonia energy is equal to 5% of the current energy demand in the future. And we use different loss rates range from 0.5 to 5% to estimate the reactive nitrogen emissions from ammonia if we are going to use ammonia energy. And so the yellow bar here shows the current reactive nitrogen emissions in those countries or regions. And the red bar is the estimated reactive nitrogen emissions from ammonia energy. And as you can see, if we assume the loss rate is 5%, the emission is going to be higher, much higher compared with the current reactive nitrogen emissions. And even if the loss rate is only 0.5%, the contribution is also still very significant compared with the current level. And so in the following presentations, I'm going to focus on ammonia, which is a major species of reactive nitrogen. So we developed high-resolution satellite ammonia map at the spatial resolution of 2 kilometers. And as you can see, in the US, right now the concentration is very high, mostly in regions with intensive agricultural activities, like Central California and Midwest US. And those white circles here shows the locations of ammonia production plants in the US, and the size denotes the capacity of those production plants. So if we zoom into the biggest ammonia production plants in the US, which contribute to about 20% of US ammonia production, as you can see here, the ammonia concentration based on satellite observations is very high, centered on this plant. And so then we apply a simple box model and assume that the lifetime of ammonia is about 12 hours. Then the emission from this single ammonia plant is about 2.3 times 10 to 6 kilograms per year, and that is equal to about 0.005% loss rate. So one of the challenging issue is a lot of these plants are currently located in regions with intensive agricultural activities. So it's very hard to distinguish its signal from the surrounding areas. If we assume that the 0.05% loss rate and extrapolate it to all of ammonia production plants in the US, the total ammonia emissions is going to be about 9 times 10 to 6 kilograms. But that is only for the plant itself and does not consider other parts of the supply chain. For example, the figure here shows the ammonia pipelines in the US, which is the largest ammonia production and distribution network in the world. So currently there are almost like no studies about the leak from this whole distribution network, and we don't know like what's the exact loss rate from it, and it's really hard to use satellite products to tell the signals from these pipeline leaks. And so if we go to the bottom-up emission inventory, for example, here we use the US National Emission Inventory as an example. There are two sectors that's related to ammonia production plants. One is industrial chemical manufacturing, and the other is unclassified industrial sectors. And the total loss rate is about 0.1 to 0.2%. So currently, it contributes to about 0.5 to 1% of total ammonia emissions in the US. And in the future, if ammonia is going to contribute to about 3% of energy demands, that will result in about 10-fold increase of ammonia production. And consequently, the total emissions from this sector is going to be about 5 to 10% of total ammonia emissions in the US. And if we use, because right now we don't have a very clear understanding of ammonia leakage from the whole supply chain. If we use methane leakage rate, which is about 1.4% as the upper bound limit of ammonia leakage rate, the current ammonia leakage is going to contribute is about 6% of total ammonia emissions, and in the future it's going to be about if we consider still the 3% of total energy demanding, it's going to be about 40% of total ammonia emissions. And so this figure here shows that both satellite and ground monitoring network shows that currently from 2008 to 2018, there are significant ammonia concentration increases in the US, as you can see here. And the median is about 6.8% per year in the contiguous US, and in the urban areas, the value is a little bit higher. It's about 8.1% per year. So, and this could have huge impacts on nitrogen depositions in sensitive ecosystems like national parks. So, and another issue is, besides the increase of annual mean ammonia concentrations, switching to an ammonia economy could impact ammonia's seasonality. Right now, because the major sources of ammonia emissions are from agricultural activities, it usually have a higher emission rates in spring and summer. And if we are gonna switch into an ammonia economy, we probably is gonna have more ammonia emissions in winter. And in winter, the low temperature and high relative humidity in general favor the formation of ammonium aerosols, and there is possible direct nucleation between ammonia and nitric acid in the urban atmosphere. So right now we have low ammonia but high nitrous dioxide in the urban areas. For example, this shows an example of the seasonality in Chicago. And in the future, we are probably going to have both high ammonia and nitrous dioxide in winter, and that could contribute to an increase in ammonium aerosols formation. So here is just a quick summary. So one of the issues is it's very difficult for us to quantify the ammonia emissions from this ammonia production supply chain right now. And the uncertainties are very high from the satellite observation estimates. And we really need input from in situ measurements like airborne measurements or like other ground measurements. And the possible environmental impacts is a shift of ammonia seasonality and the location of ammonia hotspots, which could be detrimental to the sensitive ecosystems and could contribute to the formation of wintertime haze formation. And that's it. Thank you.
Thank you, Rui. That was Very interesting. Thank you for sharing a bit of your work with us. Our final presentation is from the International Maritime Organization, Camille Bourgeon. He has been working in the Marine Environment Division in the International Maritime Organization, IMO. In his role, he assists intergovernmental negotiations on the development of the global regulatory framework and policies for international shipping on clean air and climate action. Before joining IMO, he performed operational management duties in the French Maritime Affairs Directorate, dealing with safety of navigation, search and rescue, and prevention of pollution from shipping activities. Camille, I'm sorry if I didn't pronounce your last name right, but please go ahead.
This is perfect, Stephanie. Can you hear me well? Yes? Okay, excellent.
Yes, perfect.
Yeah, thank you very much for the introduction. Thank you for the invitation. It's a pleasure to be with you today. I'm actually listening to very interesting, insightful presentations before me, and I'll be just providing you a quick summary of IMO's work to decarbonize international shipping. And as we're talking about ammonia, I'll be focusing more on ammonia, but I really would like to present a caveat from the beginning that IMO's work is really technology neutral, fuel neutral, in that it does not specifically prescribe the use of one particular technology or one particular fuel, such as ammonia. But we're really looking into, and IMO member states are really looking into all possible options to achieve the goals that are set for the sector. Let me try to skip to the next. Yes, so this is where we are. Just as it's been mentioned by some previous speakers, emissions from shipping, approximately 1 gigaton of emissions of CO2 equivalent per year, with expected emissions without additional policy measures to increase by up to 50% in 2050 compared to 2008. So that's the upper side of this chart, and what you're seeing on the lowest side of the chart is the ambitions that are set now for the sector by the IMO. The international shipping is a global sector, is a global industry, and is regulated through this UN specialized agency that is the International Maritime Organization in London. And it set levels of ambition for international shipping to reduce its greenhouse gas emissions, achieve net zero by around 2050, and intermediate milestones for 2030, 2040. There's even an energy uptake, a fuel uptake target for 2030, which is 5% of energy used by international shipping to be zero or near zero emission fuels or technologies. Of course, this zero or near zero emission fuels or technologies has yet to be defined, but I think this is where we can consider, I would say, potential deep reduction solutions to be included. And there's already a lot of efforts by the industry and by the member states in really incentivizing the use of these technologies in a safe and sustainable manner. As I was saying in the introduction, it's a technology neutral, technology agnostic approach, and so in informing the potential increased levels of ambition, we prepared a study as part of this Future Fuels and Technology project, and with together with Ricardo and DNV, we've mapped a number of potential fuels and technologies and analyzed based on literature reviews their technology and commercial readiness. And so you can see here, for example, there's several ammonia fuel pathways, but basically it shows that by 2035, in basically 10 years from now, a wide variety of technology options are likely to be ready in international shipping. And a lot of investments are already taking place in research, development, and deployment of these technologies. Now, what's needed and what IMO member states are doing now to support the uptake of these fuels and technologies, including ammonia. The first aspect is to develop the mandatory regulations that will apply to ships, and to incentivize the use of these fuels. There's different levers, different possible levers to drive the increased demand, the increase of demand for these fuels and technologies. And we have in shipping a number of international conventions and rules that apply to all ships. And when it comes to preventing pollution to the marine environment by shipping activities, we're talking here about the MARPOL Convention that has been in place for many decades, and that has a specific annex on air pollution. We're looking into SOx, particulate matter, nitrogen oxides, etc., but also the carbon intensity of international shipping. And so we had a meeting of the Marine Environment Protection Committee in just a few weeks' time, in March, where IMO member states agreed in principle that these regulations would be developed in in MARPOL Annex 6. We have quite a tight time frame. The idea is to adopt these regulations next year. And so they've agreed on the draft outline of an IMO net zero framework that will have two legs. One is the fuel mandate, fuel standard, looking into all possible compliance mechanisms, but setting really the GHG intensity requirements for the fuels without prescribing one particular type of fuel, but really setting the performance that has to be achieved. And along with these technical regulations, the member states are working on the development of a pricing mechanism, GHG pricing mechanism, to incentivize not only the uptake of these fuels, but also more largely a just and equitable transition in shipping. And this also, as you can imagine, has a lot of implications for a sector that does not yet have such a mechanism. So member states and the observer organizations at the IMO are invited to work together, and I know that they are on working towards consolidated proposal to the next session of the committee that will be in September and October this year. So as you can see from the timeline below, we are really in the middle of this journey with the development of the legal framework on the one hand, and in parallel, the assessment of its implications and impacts, and in particular, the impact of these regulations on states, on trade, on the economy, etc. Another element, which is really crucial as well, and it's been mentioned by some, is to make sure that we account and that we assess the associated emissions by all fuels and technologies in an equal manner, and having a level playing field as well in this area is crucial. So we have developed the first version of the LCA guidelines in the IMO, which were adopted in 2021, and 2023. And already this year, a revised version of these guidelines was adopted by MEPC in March. And this is the document that sets the method for how to quantify emissions from the upstream and the downstream side. So well to tank and tank to wake of all marine fuels. And we're looking into all possible fuel types and fuel production pathways. So it's for now, it's quite a long list that now needs to be filled with actual values. And we're also developing protocols and mechanism for the certification of actual emission values. So all GHGs are included with focus on CO2, CH4, N2O, but also other sustainability aspects. For those of you who are familiar with the ICAO system, it's a little bit of a similar approach where we also have a number of sustainability aspects or themes, including water, soil, conservation, etc., that has to be assessed for each fuel and each fuel production pathways. It's quite a lot of work where we need specific expertise, and the MEPC agreed to establish a new group of experts that will be established. We're actually working on it now, so it will be established in the coming few months to conduct the review of scientific and technical issues related to these guidelines. And it's being established in a well-established mechanism of the UN family called the GESAMP. It's a group of experts on the scientific aspects of marine environmental protection, which a number of, I think 16 UN agencies are part of, including UNEP, to work on assessing a number of issues in terms of their impact on the marine environment. And so they've agreed to, well, basically widen their scope of work to also LCA aspects. And in parallel, we have established working groups that are working now on social and economic sustainability aspects. I was mentioning that before. These are also important elements of the LCA assessment. And also on issues such as measurement and verification of methane, nitrous oxide emissions. And here we have there's a number of proposals to look both into test beds and actual emissions on board ships. Third leg, which is absolutely crucial as well, and it's been mentioned by some, and as you can see, all these issues are being brought forward at the IMO, which is the regulator of international shipping, its safety implications. And this is true for ammonia, of course. This is true for any other fuel or technology that is being explored as a potential for decarbonizing international shipping. And this is the Maritime Safety Committee that is in charge. They're working on, and we're working on updating the SOLAS Convention on safety of life at sea that applies to all ships trading internationally. And so now they've identified a number of appropriate fuels and technologies. So again, this technology neutral approach, and they're doing risk assessments in relation to persons, in particular the crew on board, the ship itself, and a number of associated operations, including bunkering. And they're doing a mapping, a regulatory mapping of what needs to be updated before ammonia really becomes a solution for at a larger scale in shipping. So, and specifically for ammonia, we have been working on guidelines for the safety of ships using ammonia as a fuel that are expected to be finalized this year. So this will come really in support of all the work that's been done in the industry. There are already classification societies rules, but this will be well, different because these are IMO rules, IMO guidelines, and usually in the way IMO works, recommendatory guidelines become at some point mandatory regulations after some years of experience. And one aspect actually, and one example for this is the IGC code, which is also proving the long-lasting experience of shipping in carrying ammonia as a cargo in a safe manner. And this started with voluntary guidelines a long time ago, and it's now a mandatory code under SOLAS. This is just a highlight of the next steps at the IMO with MSC in May. Work on these issues of safety, the impact assessment and impact on states in particular. Is the issue of how to model carbon revenue disbursement from shipping will be discussed in July. And in September, October, we're having the Greenhouse Gas Working Group meeting, followed by the Marine Environment Protection Committee, where we will be discussing a number of all these issues, in particular the development of the IMO Net Zero framework. And just to mention also here that we're also working on energy efficiency matters to how to improve before and in parallel with actually exploring other energy sources. One need also in shipping to reduce the amount of energy that's being used. There's really still an untapped potential for energy efficiency, energy savings. So we're working on reviewing the regulatory framework on energy efficiency, and that will be discussed in September at the IMO. I'm just doing a little bit of promotion for my colleagues' work that I have been working on this information portal. Please have a visit. It's aimed at, and it's really the first version of it that's been launched a few weeks ago, where we're trying to allow people to have access to all relevant or a lot of relevant information on the decarbonization of international shipping from an IMO perspective. There's a lot of information there. Please have a look, and more importantly, please share with us your feedback. We're really happy to take them into account in the next version of the website. With that, I thank you, Stephanie, and I'm happy to respond to any questions the audience may have. Thank you.
Camille, we have come to the end of the presentations, and I wanted to thank all the panelists for their contributions. We will now have some question and answer session. So I will start with, and I will actually invite Professor Mark Settle to join me on this to moderate the Q&A, just because we're having heavy rains in Kenya, so the power sometimes is a little bit fluctuating. I can see there that everyone's posted quite a few questions on the chat, and some have already been answered. And thank you to the panelists for taking the time as well to respond directly, including providing links to reports. Okay, so I will start with one for Fayez. It read, what assumptions did you make regarding the fraction of ammonia that is lost as nitrous oxide when ammonia is burned as a marine shipping fuel? The paper I have seen on this topic offer a range of nitrous oxide emission factors because there is a large uncertainty. What EF is most likely to be correct? Are your calculations sensitive to this uncertainty?
Thank you for the question, and it's a very relevant question. As Lucy was telling, there is a lot of problem with the transparency of information, especially the emissions from engines. You talk to different people, you get different values. You look into different literature, you get different values. So we talked to some of engine manufacturers, and these values we used is actually based on such interviews. And also these values are assumed with an SCR. That's a very important thing, because without a selective catalyst reduction, you cannot achieve such values. And regarding the uncertainty, yes, in our paper, we have considered uncertainty, but it's not shown in the results here. But we have considered some uncertainties, and how it will affect the results is also shown in our work. I know that I didn't answer it properly, but thing is that we don't have a correct value yet. It's a technology under development.
Great, thank you, Fayez. Mark, I don't know if you would like to jump in here. Or...
Yes, I would. I want you've said, Fayez, that you don't have the numbers yet. Transparency is difficult, and my question to all of you on who want to answer it is how we're really going to move that openness with getting the numbers that one wants, because it seems there's a lot of speculation at the moment on possible losses. So perhaps Vibeke, you want to come in first and say, how can we transform to a more open world with better data sharing going forwards?
Yeah, and thank you for that. And yes, I think it's really important that we have good data and transparency around this. I think a lot of it's difficult to see. A lot of the data we see today is also a bit skewed in terms of, are we talking, is it the ammonia production? Is it the production of nitric acid, which has N2O, and some of that is not with catalysts in the market. And I think most of the data we have on eutrophication and everything is really from agriculture runoff, which is also the application of fertilizer, which will be different in the fuel and the maritime sector, of course. So it's very difficult to also use our existing knowledge and data and predict that directly to the future. So I think this is where we need to be very clear on really having the input on safety regulations. We need more transparent, we need more tests, we need more data, and we need more openness around what we're doing, which is really, really important. I'm convinced that we can, do this and do this transfer, but I say ammonia, if some of these leaks were relevant and the number of PPAs, ammonia is at very low measures of PPA, you smell it. So it's really an issue of understanding, I think, some of the safety regulations around this and how we can put in place measures and also good systems, which definitely need to be in place.
Thank you. Let's just see if anybody else wants to contribute to that question of increasing openness and data gathering. Yeah, Lucy.
Yeah, I think there are kind of two things. The technical collecting of data, and we've got a lot of new technology now, so we can maybe mandate for continuous emissions monitoring SEM systems for kind of new systems, so we can capture kind of real world data. But I think we also need kind of what's the right word? Kind of the social innovation to know that this can be a problem if we don't manage it appropriately, and to make sure people care enough to make sure that we really tighten the screw on this and make sure that we don't have new entrants coming into this industry and being much more lax than perhaps the existing players, for example, or that over time there's also a kind of a temporal aspect to this of, you can have a really bright sparkling ship and system that's all operating really, really tight with an A-class team, making sure there's no emissions, but over time, more and more ships, things get older, making sure that we continue to kind of adhere to high standards. And I think that's a little bit cultural as well. So, having these conversations and saying that these environmental risks, it's important that we manage those and that we don't just brush it under the carpet at an early stage and just go, oh, agriculture's a problem, industry's less of a problem, therefore, this transition is not going to damage the nitrogen cycle. Now, I've heard people involved in infrastructure say exactly that in presentations to the public, and I think that that's dangerous. I think we should always be saying, look, this is a dangerous chemical, it does need to be managed well, and we need to manage it now well, and we need to make sure that we design a regulation that will stand the test of time and keep ourselves and the environment safe.
Okay, I'm going to pass back to Steph. I see some more comments in the chat.
Yeah, there's one for Camille. Will the IMO be considering regulations specifically on ammonia slippage and NOx and nitrous oxide emissions from the use of ammonia as a marine shipping fuel?
Thank you, Stephanie, and thank you for the question. Today, N2O slip is not regulated at the IMO level. We have specific regulations on NOx, and these regulations have been in place for a lot of time now, with different levels of stringency depending on where you are. Basically, we in certain emission control areas close to well, to the coastal regions, the NOx requirements are much more stringent than in the high seas. And on the N2O and also on methane emissions and slip, we're working on, as I just mentioned, we've just established a correspondence group that is working specifically on measurement and verification of these emissions. And actually, I encourage those of you that have a certain expertise in this area to reach out to the IMO delegation, be it member state delegation or organization, who would like to contribute to that work, because we need all the appropriate expertise to identify how to best regulate these emissions in the shipping sector.
Can I just follow up on that, Camille, which is,
Sure.
you mentioned you have a NOx regulations in place already, it's spatially variable. You don't have it for N2O. Do you have it for ammonia yet? Well, I wasn't clear
No.
on that. So
No.
neither for ammonia nor NOx, or N2O, only for NOx. And
NOx,
just
SOx,
so,
particulate matter.
exactly, just so we can understand how that works. So I think many people will be familiar with Kyoto Protocol. Many on the call will be familiar with the Air Pollution Convention, the Gothenburg Protocol, setting national limits and ceilings. Are the regulations in the IMO world mandatory to countries, or who are they mandatory to, or are they voluntary?
So many of these regulations are mandatory to ships, because the enforcement system is looking into the ship itself as an entity. So when and it applies to all ships, there's a level playing field among all ships, whatever flag they fly. So and the enforcement works primarily through the flag state, so the flag of administration of the country of registration, but also port states. So as a port state, you are you're entitled to visit foreign ships and make sure that the IMO regulations are actually implemented on board that ship. And if this is not the case, then as a port state, again, being a party to an IMO convention, for example, MARPOL, you can take a number of actions to enforce this regulation, and that can go up to the detention of the ship, and that's happening actually on a daily basis and in across the world, where port state control officers are visiting foreign ships and making sure that IMO regulations on safety, on protection of the marine environment are appropriately implemented, and if not, well, sometimes the ships are detained.
Very good. I'm going to pass back to Steph just now, but before doing so, very quick, who would be the entities needed to bring forward regulations on N2O and ammonia that are currently missing? Whose job would that be to do?
Is that for me, or is that for?
Yeah, yes, to you, Camille. I'm going to pass back to Steph after a very quick answer on that one. Whose job would need to bring that forward?
Yeah, well, so the proposals always come from states, and then it's for the IMO member states together jointly to decide what regulation they want to apply for shipping.
Very good.
Now, there's also a number of regulations that are
I'm going to pass back to
needed
Steph now, Camille.
Okay,
I just
go
because we're running short on time now, and there may be other questions. So over to you, Steph.
Sorry about that. All right. I hope you can hear me. It started raining here, so all right. So for Rui, I saw a question in the chat. Thank you very much for an excellent presentation. You mentioned that ammonia will be having 3% energy share in future, regarding this, what is your tentative year for this assumption?
So right now we don't have a very clear timeline about this, and the number comes from, we assume that hydrogen is going to be about, if hydrogen is going to be about 15% of the current energy demand, and ammonia contributes to about 20% of hydrogen storage and transport, and that's how we get the number like 3%. Yeah.
Excellent. Mark, I think we have time for one last question. As Vice Chair of the GPNM,
Yeah.
I'll let you.
Yeah,
I'll let you.
Thanks very much.
Yeah.
I make a brief comment here because it seems to me that this is a start of a really important call and a challenge of crossing these things together. Clearly, there's a role for member states. This is getting people interested. I do have one strategic question, a couple actually. One is about the satellite observations. In a preparatory call, we discussed the European Union's plans for a nitrogen satellite, NitroSat, but the European Union decided not to buy the NitroSat. So that is not coming forward, and that is still a challenge for better monitoring data coming up. So somehow we need to find a way of doing that, finding a way of investing, and it may well be that the street value of the ammonia wasted is worth the wait to get such a system in place, purely from a business perspective, just as it is with methane. It may be that somebody, if you want to react to that, stick your hand up. But meanwhile, I have one more comment, which is, should we be using catalysts to destroy this nitrogen, or should we be trying to recover as much as possible and turn it back into sellable ammonia? Presumably, we want the latter. But at the moment, catalysts just use ammonia in non-static catalytic reduction to destroy it. So we end up with nothing. So is that a position your industry, Vibeke, takes of how to transition away to as much recovery as possible?
Yeah, I think of course the value of course for us would be to have it as ammonia and to avoid really having to do sort of as much as possible end of pipe, reduction on the tail gases. But I think when you get to that and we get to combustion, if you have the tail gases, then it's difficult to do anything else than to reduce the NOxes and the N2O. So I think it's also the technology on how to avoid as much as possible on that is important.
Yeah. Okay. Understood. Take your point. So prevention is better than cure on that front. Okay. Well, I think with that, time is running, and we need to hand over to you, Ning, if that's okay, Steph.
Yeah. Just before Ning, I will just clarify two things. First of all, thank you everyone for taking the time to join us today. There will be a recording made available on the link of the meeting, of the webinar, along with a very short summary of the discussion. We're sorry if we didn't address all the questions, but it's a very interesting topic, so I'm sure we'll have more on this as well in the future. I will now invite my colleague, Mr. Ning Liu, Officer of UNEP, to provide some closing remarks. Thank you.
Okay, thank you very much, Stephanie. Dear participants, as we draw the curtains on the insightful session, exploring the potential of ammonia as a shipping fuel and its implications on the nitrogen cycle, I extend my heartfelt gratitude to all our distinguished speakers for their invaluable contributions. Profound thanks to Professor Mark Sutton for setting the tone with his welcoming remarks and moderation, and to Vibeke Rasmussen, Beyaz Malik Kanjirala, Lucy Galim, and Turner Tuttle, Rui Wang, and Camille Bergen for sharing their expertise and perspectives. The discussions today have shed light on the technology and economic feasibility, environmental impacts, and regulatory frameworks. surrounding the use of ammonia in marine transportation. While recognizing the promise of ammonia as a cleaner fuel alternative, it's imperative to acknowledge the associated environmental risks and adopt precautionary measures. The insight shared today underscored the urgency for member states to collaborate on sustainable nitrogen management, aligning with the resolutions of the UN Environmental Assembly. As we navigate the complexity of nutrients pollution and strives for sustainable solutions, the collaboration between academia, policymakers, the private sector, NGOs, media, and the civil society become paramount. Let us seize the opportunity to forge meaningful partnership and work collectively towards addressing the challenges ahead. In closing, let me express our unwavering commitment to fostering dialogue, driving innovation, and advancing sustainable practices in the realm of marine transportation and nitrogen management. Together, let us chart a course towards a healthier, more resilient future for our planet. Thank you once again to all our esteemed participants. Thank you.
Thank you,
Thank
everybody.
you.
Have a good day. Thank you.